Okay, everyone. Sorry I'm running late today. So we've got, I was looking at the schedule, we've got today's lecture and 2 more, and then we're done with the semester. So I plan on, I'm going to briefly review control theory and just make sure everyone's in good shape with that. Then I'm going to talk about the next lab, which I just got done, and then we'll cover real-time scheduling, and then that'll be the last topic, and we'll have our final exam review on the 25th, which is our last class. Okay? So hopefully you remember to take the quiz on control theory. We finished up that topic last time, but I kind of blew through the second half pretty fast. Just to quickly review that, we talked about PID controllers, proportional integrative derivative. And these are, in the S domain, these are pretty simple. It's just a proportional parameter plus S times a derivative parameter plus 1 over S times an integral parameter. Right? And then you can, the idea is that you would use this as a controller in a closed loop feedback controller. And then, of course, you can leave off, like, for example, you can create a PI controller. You can take the derivative off if you want. And so in this case, we had this example where we have a plant, which I was using the plant from the moving the coin physical example, the controller, which is a PI controller, and then we created the closed loop feedback. And for that, it's basically the open loop transfer function, which is GC times GP, and then you would put that into its closed loop form, which is 1 over plus the open loop, right? Make sense? Sorry, I scratched that. It's the open loop over 1 plus the open loop, right? Sorry, is the closed loop transfer function. And then, of course, to create the open loop transfer function, you just multiply these 2 guys in the S domain. You just multiply those two together. And so I went through the derivation here. I kind of didn't want to spend too much time on that, but basically the idea is that I wanted to pick, in this case I was trying to solve for to find, values for Kp and Ki. In practice, though, usually you would tune those, right? You would change them around and try to get a good response. It's usually kind of an iterative process. Okay, so I calculated the impulse response of the closed loop impulse response, and I talked about how there's this rise time and overshoot. This is the step response. And this step is actually the input, the set point. So this is the RF. So we're putting a step in for RF. So the idea is that the coin is in one position and we want to suddenly move it to another position. So this is the input to the closed loop transfer function. And the output is actually this signal, which represents the position of the coin. So we have the position of the coin here, we have the force that we're applying to the coin here, and we have the error signal here, which is how far away the coin is to where we want it to be, right? And so when I plot them, I'm just plotting 2 of these signals, which is the reference and the position of the coin. And the reference is a step function. And the reason I chose a step function was because, actually that's an impulse function there. The next slide has it, yeah. This is a step function. So there's 2 reasons we chose a step function. One is it shows that the system is stable because a step contains all the frequencies, right? And 2, because it's a similar type of thing that you would use in practice. You'd say, I want to move the coin, so this blue line would represent, the old position I want the coin in and the new position I want the coin in. And then this yellow line shows how closely the system tracks the set point, right? And you can characterize that with rise time and overshoot. Overshoot is, sometimes you may not care depending on the application, but the overshoot is how far past the line we go. Rise time is how fast it takes, or how long it takes to get the coin to meet the the set point. And then tuning, I mentioned we can manipulate these values and get different rise times and overshoots. Okay, and then I talked about the zdomain, which is a discrete time. So, I don't know, you guys probably didn't talk about discrete time in robotics, right? You did PID controllers. So there's two ways you can approach this. You can kind of hand wave it, I think, although I've never done it this way. I think you can just write a program that does a PID controller and just hope that it works.
That's what we did.
Okay, yeah, so that's one way to do it. However, you're not really, so the problem is that you're not, these S-domain transfer functions are continuous, these are continuous functions, so you can't implement those on a computer unless the computer was kind of infinitely fast. Would be able to update its output infinitely fast in 0 time. You guys, I'm sure by now, with the labs we've done in this class, you know that generally you have some time step that you're trying to match on a controller, on a processor. So you say, I want to update the output of this controller once every n seconds, right? Or a certain frequency, like 100 hertz, 100 times per second. I want to update the output of the controller, right? You guys with me? So that's the time step, or the sampling time, or the sampling frequency, right? And so in order to do that, in order to do an analysis of that sort of discrete time system, you have to use the z-domain, not the s-domain. So the z-domain is kind of like the s-domain, but it's kind of different. It uses z instead of s. Often the notation is a little different. Usually you'll have the signals have brackets instead of parentheses because it's not really time-based, it's sample-based, right? And the most interesting thing about it, this is the part that I think is cool, is that the inverse, so how did we do the inverse S transform? We had to do the eigenfunctions, right? We had to put it into a specific form and do the inverse Laplace transform. That was actually kind of hard to do. The inverse Z transform is actually a little bit more convenient, assuming the only restriction is we have to get the z-domain into a form where we have powers of z multiplied against signals of z, right? So if you have z minus 1 times x of z, where x of z is a discrete signal, this simply represents the last sample, right? So if you were to convert this into the time domain, or I guess you call it the sample domain, this would become that, x of n minus 1, if n is the current sample, one sample ago. You guys with me? Okay, so the problem though is if you want to convert from S domain to Z domain, you can't just convert it without knowing the step time, the time step, right? Because you actually get a different Z domain version of an S domain function depending on the sample time. You guys with me on this? Right? So hold on, sorry. So you do this thing called there's different ways to do it, but one way to do it is the tustin transform, where you replace the s's with 2 over t sub s, where t sub s is your sample time, times z minus 1 over z plus 1. So in other words, if you were converting an S domain transfer function into Z domain, you could do different types of transformations with different TS's, right? Depending on how fast your controller is, how fast your controller updates its control value, right? You guys with me? Okay, so that's the idea. Okay, now I mentioned that I also went through this, what is in a Z domain, what's an integral and what's a derivative in the Z domain? What does it mean? How do you, well, the derivative is called the first difference, and it's z minus 1 over z. right? But if you can transform this into 1 minus z minus 1, right? And if you look at it, and see, this form doesn't make any sense to me. I don't know what the heck's that, z minus 1 over z, why is that the derivative? But if you look at it in this form, you see it's 1 minus z to the minus 1, which is saying that the derivative is the current sample minus the last sample. So it's the difference between the current sample I'm seeing and the last sample. And that makes sense as a derivative, right? The integral, though, is a little stranger. That's z over z minus 1, which is kind of just the inverse, right? Literally just the inverse of the derivative. Z over z minus 1, which that one is, it's a little strange, but you can actually figure that out by doing this division. And it turns out to do this division and to get it out of this form and to get it into a form that looks like something that could be more easily interpreted in the time domain, you end up with an infinite series. It's 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3 forever, right? Which also makes sense for an integral, right? You're adding up all the samples you've seen since the beginning of time till now. That's the integral, right? So that's the z domain integral. Okay, so I think that's mostly, and by the way, the time domain version of the z transfer function is how you would implement this in code. So if you're writing code, you would want to get it into this form here where, not that form. Oh yeah, that form. Yeah, this form, right? Where you're saying y of z is your output and u of z is your input. And so this is saying that the current output is going to be 1/6 of, oh, sorry, that's not the, no, sorry. Yeah, sorry. Yeah, the current output is going to be 1/6 the input, so the current input sample, plus 1/3 the previous input sample, plus 1/6 2 input samples ago. And then you see this thing where it's like, oh, it's 4/3 the previous output, plus 1/3 the 2 outputs ago. And so this, actually, what we end up with here is a time domain representation of the transfer function where we don't have to add up every input we've seen from the beginning of time, because that integral actually collapses into this form where we can look at previous outputs. Yes?
So there's something that's a little bit confusing me on this, which is, I guess, in the theory of it. Computers are discrete. So what I'm kind of asking is, what is the reason that this is important? Like you said, in robotics, we were using continuous and just hoping it worked.
Yeah.
So are you saying that like using the S version introduces error because the function can actually do that?
Yes. Yeah, that's right. Yeah, so I'm not sure how you did it in robotics, but I remember when I was in grad school, we had a robotics course where they did it a similar way, which is where they sort of just used trial and error. So they wrote code that calculated the derivative as, I think, the current minus the last sample, I think. Although I think you could probably do that in different ways. But the most straightforward way is like, I'm just looking at the change in input, which is the current input minus the previous input. And then the integral, you probably just used a summation, like a running sum. And then you just did you multiplied by your 3 values, and then you just hoped it worked. But if it doesn't work, then how does it not work? Well, it probably, it's unstable, right? That's usually what happens. You implement it and the robot just goes scooting across the floor and it doesn't do what you want it to do, right? So if you're doing an analysis and you want to try to pre-design your controller without using, the sort of trial and error approach, then you'd want to represent your functions in the Z domain with a given time step, right, for your controller, right? Because by integrating the time step in there, you can kind of predict whether the controller will be stable, mathematically, right? Even if you have an S domain physical model, like physical models are usually S domains, right? Because the robot motor is continuous, right? But you can you can convert the robot model into a discrete model, right? And you can convert your S-domain PID controller into a discrete model, and then you could simulate the whole thing in the Z-domain. And this is actually what MATLAB does, by the way. When you run an S-domain system in MATLAB in Simulink, it's converting it internally to a discrete. There's a runtime environment that's doing that, and it's giving you a discrete approximation, because even in a simulator like MATLAB, it still has to do this conversion internally to do S-domain, to do continuous transfer, continuous dynamics. Okay. Now you could also do. There's also this thing. There's also a state space representation, which is where instead of using Z-domain, you can use state space, which is where you essentially keep everything in the time domain, but you can have state variables that are derivatives and integrals. But that's outside that's another approach. I'm not going to cover that in this class because I just wanted to give an introduction. But there's other ways to discretize continuous systems as well. Okay. So then I just showed some examples of that stuff. Okay. So any questions? Those were the main points I wanted to get across: the difference between S-domain and Z-domain, and how to do the conversion, and of course the closed loop controller. Okay, so now I'm going to skip over to the lab. So lab 4 will be our final lab, the final project. I got the impression that the previous lab, hold on, let me download this. I got the impression that the previous lab went pretty well. And like I said, it was the first time. I'll open this with Acrobat. That last lab was the first time we've ever done a software and hardware in one lab together, working together. Sorry. I need to sign into Adobe. Okay, never mind. All right, in this lab, this will be our final lab. My goal in this class was to get to a closed loop control system, but I always wanted to do an open loop one first, because I think doing a closed loop controller, initially would be too much. So, and unfortunately we won't have time to do a closed loop, but I think my objective here is just do an open loop controller for this last lab, okay, because I don't want to. We only have 2 weeks, and I know you guys have other projects, so I don't want to give you too much to do. But I think this will still give you a nice, it'll be a nice experience in hooking up something physical to the FPGA boards. So in this lab, we want to design an open loop controller for a motor. I got these motors, and they're just small electric DC motors, and they're comprised of a motor, and they have a gearbox on the outside, and this gearbox reduces the speed. There's an internal shaft in the motor that spins, and then this thing reduces the speed by a factor of 50. This is a 50-to-1 gearbox. So it decreases the speed, but it increases the torque. You can buy these with different gear ratios. I just happen to get the 50-to-1. It was a nice kind of in-between. And then also, there's an encoder built into this that uses the Hall effect to basically measure the speed of the motor. And that's what we want to be able to read with the FPGA. But the encoder is a pulse-based encoder, though. So instead of telling you the position of the shaft, it gives you a pulse, it gives you a square wave. And all you have to do is measure the frequency. Or the period, you could just measure rising edge to rising edge, right? And then you just do a simple calculation to convert that to RPMs. Okay, so it's a digital signal, single bit digital signal. Okay, and that's how it works. So we want to be able to drive this motor at different speeds with the FPGA and just read the speed. That's the objective. We're not going to try to control it and get to a specific speed, because for that we'd need a closed loop. Okay, make sense? Okay, so now how do you control the motor? Can you connect the motor directly to the FPGA for controlling it? No, you have to use, the FPGA cannot power a motor. We need a power supply to power the motor. And we have power supplies in the lab. Those big, we have really nice ones. They're like those big power supplies. Also, the motor one's 6 volts, and the FPGA board just has 5 volts. So we're going to hook up the power supply to a chip called an Hbridge. And then the Hbridge will be the power behind the motor, and we'll control the Hbridge using a PWM signal, just like you did with the LEDs. Okay, now what is an Hbridge? An Hbridge is a very simple circuit that looks like this. You have a voltage, which is the top and bottom rail. Bless you.
Thank you.
You have a voltage here, right? In this case, we're going to have 6 volts. And then you have this shape that looks like an H with 4 transistors, and they're arranged like this in the H. In the middle of the H is where you have their device that you're powering, right? Your motor, right? So these 2 terminals are the 2 terminals on the motor, the 2 power terminals. Okay? The idea is that you're either going to have switch 1 and switch 4 on, right? In which case it creates a path from the supply like this down, and these other 2 switches off, right? Or vice versa, where switch 3 and switch 2 are on, and you have a path from power to ground through here, right? So there's only 2 configurations. You can either have these 2 transistors on or these 2 transistors on. You don't want to have them both on. That's no good. I mean, both sides on, right? So you have like 2 legs. You have one leg on and the other. Does that make sense? Now, what's the point of that? Because either way, you're going to have 5 volts, right? Or 6 volts, assuming you have 6 volts. What's the point of doing this? Why? It's because the current will flow through from left to right if you have switch 1 and switch 4 on, right? But if you have switch 3 and switch 2 on, the current's going to flow from right to left, right? So in other words, the voltage is actually either going to be positive or negative, depending on which pair of transistors you turn on, right? And that's how you get the motor to go forward or backwards, right? Because you give the motor a positive voltage to go forward and a negative voltage to go backwards, right? Now you might say, okay, that's fine, but that's just like one speed, right? You either go full speed forward or full speed backwards, depending on which pair of transistors you turn on. And the way that you get around that to control the speed is you put a pulse width modulated signal, just like you did with the LEDs on the previous lab, the previous 2 labs, right? So if you turn off transistors or switches 2 and 3, if you turn these guys off, and then you do a PWM on the other 2 transistors, S1 and S4, right? Then if you have a 50% duty cycle, for instance, and if, say, this is 6 volts and this is ground, then you're going to have a 3 volt, effectively 3 volts, because you're turning on 6 volts and turning off 6 volts 50-50, right? So the motor is going to see this switching on off on off on off on off on off on off. But if you have it on half the time and off half the time, it's effectively delivering half the power than you would if you just had S1 and S4 on, just on, right? You guys with me? So this way we can control the speed and the direction of the motor by essentially just sending a PWM signal to two of the transistors and the other 2 being off, or vice versa, right? You guys with me? And so that PWM signal is just digital. So we have a digital input into the Hbridge, and we have a digital output from the motor to the FPGA, which is the encoder, which is just a square wave that gives us a frequency. And we interpret that frequency as a motor speed. That make sense? Okay. Now, also, you might say, wait a second, how do we know the direction of the motor from the encoder if the encoder just gives us the speed? Well, you might say, well, we know the direction because we know which way we're telling the motor to go, right? We're either telling it to go forward or backward, and so obviously we'll know. But that's not really good, though, because if you were to switch the motor direction really fast and suddenly, it would take the motor some time to physically slow down, and then start going the other direction, right? So we don't want to trust the controller to tell us the direction. We really want to get that from the encoder, right? So we want to know from the encoder which direction and the speed of the motor. And so the way you solve that problem is the encoder actually has two outputs that are out of phase from one another about 180 degrees. So basically what you're looking for is the rising edge. You could just look for the rising edge of one of the two outputs. And when you see that rising edge, if the other one is low, you know it's going one direction, and if the other one is high, it's going the other direction, right? Because they're complemented each other, right? Make sense? Yes?
What happens to the system if you turn on S1 and S2 or S3 and S4 at the same time?
I don't know. It wouldn't be good. Okay. It would probably fry, yeah, it'd probably fry the Hbridge, I would guess, but they may have some protection in there against that. In fact, I think the data sheet mentions something about that, but I have to look at it. By the way, I put the data sheet on the Dropbox. If you go to the Dropbox and you look, there's Lab 4 data sheets. This is the DC motor. Unfortunately, a lot of it's in Chinese, so it's not super helpful. I had to figure this out kind of. Yeah, I didn't find anyone that could translate it, but it's basically just, here's the main table, and so there are 6 wires on the motor, and they're actually labeled in English on the connector on the silk screen on this little circuit board. So it says M1 ground, C1, C2, VCC, and M2. So M1 and M2 are the that's just you connect directly to the Hbridge. So M1 and M2 on the motor are these two terminals, right? So the Hbridge exposes these two guys, and you connect those directly to M1 and M2 on the motor, right? So that's easy. That's just wire them up. Then you've got ground, which goes to ground. So there's a ground and there's a VCC. So these just go straight to the power supply, 6 volts. So that takes care of 4. The other 2 are the encoder, C1 and C2. That's the encoder I just talked about. That's an output signal, digital output signal. So it's pretty straightforward to hook up. There's basically just 4 pins that go to your FPGA, and then 2 are power. This shows the waveform of the encoder, but this is really misleading because if you look at this, it says the period is T, right? And then it shows this is one encoder signal and the other encoder signal, right? And then it says the difference between the rising edge of one encoder and the rising edge of the other encoder is 1/2 T, right? Well, if this is T, 1/2 T would be like that, right? But yet, if you look at what they've got there, it's much smaller than that. So this actually doesn't make any sense. It's not to scale. I mean, what they should have did is they should have had, this should have been moved over, right? Because they're 180 degrees out of phase, right? Because the duty cycle of this guy is 1/2 the period of the one on the top. And they're both, as far as I can tell, they're square waves with a 50% duty cycle, right? And one has a duty cycle of 1/2 the period of the other, so they should just be complements of one another, right? Okay, but that's not what is shown here. This is way misleading. But yeah, it's actually really easy. You just, the way I coded it when I did it was I just looked for the rising edges of this guy, and whenever I saw the rising edge of one, I just looked at the value of the other one, and if it was 0, I knew it was going one direction. If it was 1, it was going the other. So the logic is very simple for that. Okay, so now how do we connect to the FPGA? The FPGA has this, what they call an expansion header. I call it the GPIO connector. It's a 40-pin ribbon cable connector. It's really easy to use because in your top-level design, you just create a port on your top level thing called GPIO. And it's 36 pins, 35 down to 0. And that's it, done. You've got it in there. Now you might say, wait a second, if it's a 40 pin connector, then why is it a 36 pin connection? Because 4 of these guys are not signals. You've got a 5 volts coming out of here, a ground, a 3.3, and a ground. Okay, so this is important because the FPGA, so the motor is on a 6 volt power supply, right? That's your power supply, your lab bench power supply. But it has to talk to the FPGA, which has its own power supply, right? So in order for that to work, you have to make sure that you short the ground on the FPGA board, which is exposed on this connector. You got to connect this ground to the ground on the power supply, so they share a common ground. That way, when the motor, which just sees the power supply, sends a digital signal over to the FPGA, they're in reference to the same ground, right? So they can talk because it's a single-ended input, meaning that the signals are referred to ground as opposed to a differential where the voltage would go plus or minus over 2 wires. You guys with me? Okay. Okay. So, and by the way, we only need 4 of these other wires. We have 36 pins. You only need 4. All right. There's the Hbridge forward and backward pulse width modulation signal, and then there's the encoder, 2 encoders. So you only need 4 of these out of the 36. So you need 4 of these guys, and of course one of these grounds you want to pick up. By the way, you cannot power the motor. I know that because I tried. I tried this, it didn't work. You can't power the motor off of this 5 volt pin. There's not enough power comes out of this to power that motor. Even though it's a little tiny motor, it still is not enough. This thing is not intended to be to drive a motor. So don't use that. Use the big power supplies. Okay, so now this is a little sloppy. I apologize. I tried to make this as easy as possible. It's a little hard to read. We used to have a tool called fritzing that was able to build nicer diagrams. But basically, I color-coded the wires so you can kind of see what's going on. But here's the motor, here's the power supply, here's the expansion header, and here's the breadboard. So you just take a breadboard, and the Hbridge is here. The Hbridge is a 8-pin DIP package. So you just plug the Hbridge into the breadboard. You guys know how to use breadboards, right? So you plug it in over this, you have it straddle this middle thing, right? And then I don't know if this is the best way to do it, but I used the power supply rails on the breadboard, this upper 2 rows. So I connected the power supply. Power supply has 3 channels. I connected channel 1 down here to the plus on this guy, power supply rail. And then of course the ground to the ground side. And then this ground I also brought over to this ground on the expansion header. So this creates a common ground between the breadboard, the power supply, and the FPGA board, right? And then all of the stuff, or the Hbridge and the motor, I just connected to the 6 volt supply here. And by the way, 6 volts, you have to dial that up here. You just type in 6, you hit channel 1, 6, 0, 0, enter, on. That's it, to power that up. And then the other nice thing is that once you do that, this will also monitor the amount of current coming out. And you can actually see, like when the motor starts spinning, you can see the current goes up and then it comes back down when you spin it down. It's pretty nice. So pretty much the motor has the 6 pins I mentioned. There's power and ground. So ground is black, power is red. So you can see here's black goes to ground, red goes to VDD. Yellow is the encoder, and orange is the Hbridge, both sides of the Hbridge. And then the Hbridge has its own 2 VDDs and 2 grounds. Make sense? So there's 8 pins on the Hbridge. You got 2 powers, 2 grounds, that's 4, plus the 2 going to the motor. That's 6. Oh, and then the 2 going to the FPGA, which is the PWM. Make sense? So we have all the parts for this. The breadboards are in the little kits down there. And this part should be hopefully be pretty easy to assemble. The only problem is I tried to get a ribbon cable breakout connector for a breadboard. I ordered some, but as it turns out, they weren't designed for these kind of breadboards. They were designed for the prototyping breadboards, the ones that you solder. So unfortunately, the only way to connect to this guy is just through wires. There's a female wire you can push on there, and then it has a male side you put in there. It's not ideal, but I haven't found a better way to do ribbon cable to breadboard. Okay, any questions about that? Okay, so what is the objective here? The objective is to write a program that will put out two pulse width modulated values, which I interpret as being -1 to +1. -1 being 100% duty cycle on the negative side of the Hbridge, right? And then +1 being, basically full speed forward, -1 being full speed reverse. So we want to use the FPGA, the NEOS processor, to generate a sample signal, an input, which starts at 0, goes to 1, goes down to -1, and then goes up to 0, right? Just to generate this. And then we want to measure the speed of the motor. And so I did that that's the rotational speed. So the input duty cycle is blue, the rotational speed is orange, and you can see the speed is a little wonky. It kind of goes up. Well, first of all, the speed stays 0 until the duty cycle hits about 0.3. The motor won't even turn until the duty cycle is about 0.3. I don't know why that is. I guess that's typical for motors. It just won't even engage. But once the duty cycle gets beyond about 0.3, then you can see it starts climbing up pretty fast. But then it gets up here to about, this is using this axis, so it gets up to around about 75 or 80 RPMs, which isn't that fast, but keep in mind this is the speed of the external shaft. The internal shaft is going 50 times faster because of the gear ratio. But anyway, it gets up here and then it kind of wobbles around here, right? Now, problem is, this is a result of the encoder. The encoder is a Hall effect encoder, and Hall effect encoders apparently, as you get faster, they start to have this like quantization error, like resolution issues. I don't know exactly what causes it. This is what I saw in mine. Maybe you guys will figure out a solution. But basically, you end up with these discrete values that kind of alternates between, right? It's not very smooth once you max it out. And you'll notice too, by the way, that it sort of maxes out right around 0.6 duty cycle. So pretty much 0.3 to 0.6 is kind of your usable range. Anything beyond 0.6, and it kind of just saturates, right? Again, I don't know why. I just bought these. It's the first time I did this. So basically, the way I got this plot was I ran it and I dumped all the data to the terminal, the NEOS terminal, and I just dumped the terminal to a file, and I just read that file into MATLAB and hit plot. And that's what it looks like. But you can see that it goes forward, and then I hit backwards, and it goes backwards. Right? Yes?
Do you know if it's a measurement error, as in the motor is actually going faster than that, or if it's a measurement error, as in the motor is somewhere in that range? But
it's a good question. I don't know. One thing that's strange, though, is that notice that the max speed is about 100 RPMs. But if you look at the data sheet for the motor, the data sheet, I don't know if it's on this one. No, it's not on this one. Adafruit. I got it from Adafruit. Adafruit motor with encoder. I think it's on there. Yeah, it's this one. This is the motor. Oh, it's not on here. Maybe it was on the data sheet. Yeah, maybe it was on the data sheet. Anyway, the data sheet said it was supposed to go like 200 RPMs, so, and we're only getting 100, which is strange. I think that it might be a measurement error, because it doesn't line up exactly with what the data sheet says we should be getting. I thought for sure it was here. Yeah, I don't remember what it is now, but yeah, it was basically, I don't remember where I found it, but I thought this gearing, the 50 to 1 gear ratio is supposed to go up to 200, and we're only getting about 100. So I don't know what's up with that. And I got the voltage matched. I mean, the voltage it's not like it's 6 volts. It could be the Hbridge isn't able to provide enough power to the motor. I don't know. I haven't tried that, but anyway, the objective is to just essentially produce this experiment where, you know, we just give it this input and we measure the output, right? And so now once you have this, by the way, you can feed this into MATLAB and you can have it generate an S-domain model or a zdomain model of the motor, which was my objective, and I did that. But like I said, I think we only, with 2 weeks, we don't have enough time to close the loop. But you can use this as characterization data to find the transfer function of the motor. You can also use a step function and other types of functions here too. In this case, we're giving it a sawtooth. Any questions about that? Now, where does this data come from, by the way, this blue line? How are we getting that? Well, it's going to be it's going to be the same way that you did the previous labs. You just use the performance counter as a 50 megahertz reference, and from that you can have it generate this signal. Notice this is the horizontal domain is time in seconds, so this took 25 seconds. So over the course of 25 seconds, you want to generate this sawtooth pattern and just measure the results. And then the results should be dumped to the terminal. So you just want to log these to an array, and then when it gets done with the 25-second run, you just have it print to the terminal. And then you can capture the terminal. You just type neos2-terminal greater than sign file, and it'll capture the data. Okay, any questions about that? Okay, so lab sheet's online. I'll talk more about it in class, in lab. And as with the last lab, I'll probably end up refining this. We might come out with a better version of this, but this is the initial version. It's up online. We might, add some clarification, but all the information is here, and the lab sheets are on the website. Okay, all right. So let's move on now to the next topic, which is real-time scheduling. Okay, so when you build these controllers, you have a time step, right? And so you're doing things at the beginning of each time step, and you want the CPU to finish whatever work it has to do by the end of the time step, right? So it can have this regular period, right? And you might say, what work is it doing? Well, it's doing the zdomain transfer function, right? Doing a calculation, right? There's more sophisticated control algorithms too that you might be doing. The point is that you have this deadline according to the period of the controller, and so that would be, for that, is use a real-time operating system that has a real-time scheduler. Now you can't use a regular computer, a regular operating system. And the reason is because Windows and Linux and Mac OS, they assign work to processors, right? And they ensure that the processors are allocated fairly among all the programs that you have running, but they make no guarantees whatsoever about how long it'll take to run a program. Right? So if you were to use like Mac OS to do a real-time controller, there would be no guarantee that it would get the work done within the amount of allotted time for that control period, right? And then you may miss a deadline, right? You may miss a control cycle, and then what'll happen? Well, the controller you designed with the tustin transform, in which you set T sub S, is no longer valid, and the system may become unstable, right? Make sense? You guys with me? Right. So now we don't have that big of an issue with the FPGA because we're not running an operating system. We're running a bare metal system where the software runs directly on the CPU with no operating system involved. So there's no scheduler. So the way that you guys will have your code on this project is you just run everything in a while loop, and in order to synchronize the system, you can just put a busy wait where you wait for the performance counter to reach a certain value. You just kind of wait, right? So there's less uncertainty with a bare metal system. And in fact, most controllers are built with a similar kind of bare metal system. They don't have an operating system. The problem is a general purpose computer has uncertainties in it about runtime. And the reason those uncertainties come from, what do you think they come from? I mean, they come from, you always have a sort of a different set of tasks running, right? You also have things like cache misses and interrupts. We talked about interrupts at the beginning of the semester. That's when a peripheral wants attention. It gets the CPU's attention, like a network packet arrives or someone hits a key, right? Those are all unexpected events that require the CPU's attention. There's also things like page misses. You guys, how many of you have taken 311? Okay, so you know about page misses and virtual memory systems. There's hard page faults and soft page faults. Hard page faults are when you go out to the disk and get data. Soft page faults is when you just have to do a page replacement in memory. Those all take time. There's TLB misses. There's a lot of unexpected things that happen, and so the runtime is very very uncertain, right? But what if you know the deadline? So, okay, wait, let's talk about runtime for a second. So there's this notion of worst case execution time. So if you have a process, you run it on a machine, and you run a whole bunch of times, the amount of time it takes to run is different after every run, right? Why? Because of all these uncertain things that happens. Also, sometimes programs are written in a way where you've got, if statements where depending on the input values, they may take longer depending on their path through the if statements, right? They may have dynamic control flow, right? A zdomain transfer function wouldn't have that because you just always do the same thing. You just do the same multiplies and adds every time. But some more complex controllers may have, if statements in there. They may have, their runtime may depend on the input. So the problem is that you really can never know how long it takes to run a program on a CPU, no matter what you do. Because even if any CPU, even without an operating system and with all the interrupts disabled and no virtual memory system, there's still like cache misses you have to contend with, right? You guys with me? So there's no way to ever know how long a program takes. So one way to approach this is you can approach this statistically. You can run a program a whole bunch of times, and you can calculate the average runtime and the standard deviation. And assuming that the distribution is Gaussian, right, which it may not be, especially if there's different operating modes depending on the inputs. The program may take different paths depending on the inputs. But if, for example, if it's a Gaussian distribution like this, then you can say okay, the worst case execution time is 2.326 standard deviations above the mean, and I can say that would be the worst case execution time with a 99% confidence, right? Likewise, you could say if you have 3.719 standard deviations above the mean, that'll give you a worst case execution time with 99.99% confidence. You guys with me? And again, that's assuming that we have a normal distribution here. Now, another option is you may say something like this, where you may have a mixture of Gaussians. Like in this case, we have two Gaussian distributions here that represent different paths through the program. And we could, model each of those as a Gaussian distribution, right, and calculate its mean and standard deviation. You guys with me? Okay, so let's just take a simple example. Assume you measure a task's execution time for 10 runs, and you see 12 milliseconds, 13 milliseconds, 10, 14, 11, 30, 27, 25, 31, 32. So I run it 10 times, and what's the worst case execution time at a 99.9% confidence, assuming there's a single normal distribution? And so it's pretty simple. You just calculate the mean of all those values. Of those 10 values, it's 20.5 milliseconds. The standard deviation is 9.2. And so the worst case execution time at a 99.9% confidence is going to be 20.5 milliseconds plus 3.09 times the standard deviation, which is 9.2, which is 48.9 milliseconds. So we'll just assume that's the worst case execution time. Yes?
3.09 is 99.9% converted to, what's the word for it? That's the number of standard deviations away from the mean that would be required to be the 99.9% case.
That's right. Yeah, I got that out of a table when I did these last year. I just looked it up. I didn't calculate it.
Yeah.
Okay, well, how about what happens, though, if we assume instead that the first 5 runs and the second 5 runs actually came from two separate distributions? Right, based on the program being in kind of 2 modes, right, when it ran, right? One mode being, sees a certain input beyond a certain threshold and it handles it one way, otherwise it handles it another way. So in that case, I can just calculate the mean of the first 5 observations, which is 12, and the standard deviation of the first 5 observations, which is 1.6. And then the mean of the second 5 and the standard deviation of the second 5, which is 29 and 2.9. Right? Now what happens here is that because I'm fitting 2 distributions to this data, I get a smaller standard deviation for both. And that way, I can calculate the worst case execution time of the maximum of the 2 distributions. Right? So in this case, it's the maximum of the first mean, 12, plus 3.09 times the first standard deviation, or the mean of the second group of observations, which is 29 plus 3.09 times its standard deviation, which is 2.9. And it turns out that answer is 38. So remember, when I considered all these together, my worst case execution time was 48.9. So if I treated this like a black box, right, I didn't know how the program worked at all, and I just gathered them all into one big lump, I was saying that the worst case execution time is 48.9 milliseconds. But when I consider, if I know the program has two operating modes, now I have a better estimate of 38 milliseconds, right? Does that make sense? Now this is still kind of a fairly simplistic way of looking at runtime, but it's for control programs, it's not, controllers, if it's just a PID controller, then it may be reasonable to do it this way. Okay. So what's the point of that? The point is that it's not really straightforward to calculate execution time on a CPU. Now, how do you get a standard deviation of 0? How can you make a control algorithm that's absolutely deterministic in the time it takes to run? Well, you build it in System Verilog. If you do it in System Verilog instead of C code running on a CPU, right, then it becomes deterministic because you know exactly what happens in every clock cycle. Right? If you're running it on software on a CPU, there's uncertainties in a CPU, right? So you never really know how long software takes to run, but if you design it in System Verilog, you know exactly how long that's going to run, down to the cycle. So that's the reason why a lot of people design controllers in FPGAs in System Verilog, because it's deterministic. Okay, so what about scheduling? So what's the idea with this? Well, assume that you have, let's assume for a minute now, that you have multiple tasks. When I say tasks, these are control algorithms, controllers, control tasks, right? You have 4 control tasks, but you only have one CPU that you want to use. So you have to schedule tasks. This is pretty much the same as any CPU in operating, right? Because most computers computers all have the ability, at least modern operating systems, have the ability to run more programs at the same time than you have processors, right? They schedule, right? There's a scheduling. The processors are shared, right? So this is what I'm talking about. In this case, let's assume you have 4 tasks and you have one CPU, but each of these 4 tasks have a different deadline. Well, what's the deadline? Well, the deadline is the period, the control period, the T sub S, right? We talked about the tustin transform. This is how often you have to, this is the time that you have to make a decision, a control decision, or else the system blows up, right? So these are like hard deadlines, right? And each one of these has a computation time. Now, obviously, the computation time has to be less than the deadline, or otherwise it's impossible. But even if it is, it's not necessarily an easy problem to figure out what order to put these on the CPU in order to meet all their deadlines, right? You guys with me? So we got a 40 millisecond computation time with a 76 millisecond deadline, 6 millisecond computation time with an 84 millisecond deadline, 14 time, 35 deadline, 20 time, 37 deadline, right? So there's 4 different tasks, and now I now have to figure out, like, what order do I assign each of these tasks to the CPU, to the one CPU. Now again, I'm assuming I have a single core. We'll get to multi-core here after this, but let's look at the simpler case of 1 core. 4 tasks, 1 processor core. So if you look at the way you can assign these, if I have these 4 tasks, I'm going to assume, again, I have 1 core, so I can only run one of these one at a time. And the way I show which one I'm running is through this little timing diagram where I show whichever one of these is high is the one I'm running, right? And I can only run one at a time. So at any moment in time, only 1 task is running and the other 3 are asleep, either because they're completed or they're not. I haven't run them yet, right? So how many possible ways can I order these tasks? Well, it's n factorial, 4 factorial. There's 24 ways that I can order these to run. But my objective is to run one at a time to completion, and I want them to all meet their deadline. Okay, well, let's just assume, let's do a full enumeration. Let's assume I run task 4 first, then task 3, then task 2, then task 1. Well, if you do that, task 1, I have a little red line. I don't know how well you can see that. I have a little red line with the deadline, right? So if I run task 4 first, obviously it meets its deadline because it's the first one. But the problem is I run task 3 next, but it has to wait till task 4 is done, and it meets its deadline, right? Then I run task 2, and it meets its deadline. And then the last one to run is task 1. I run it, but then it misses its deadline. It gets done after the deadline, okay? How about I do task 4, then 3, then 1, then 2. So what if I swap 1 and 2? If I do that, then all 4 make their deadline, right? They all make it. And then here's number 3, where I go 4, then 2, then 3, then 1. Task 1 misses its deadline. And then I try a bunch of other ones here. The rest of there's 24, so I try the other 21. So task 1, 4, 2, 1, 3. Now I missed on 3. 3 was way past his deadline here, right? So I try all of them, and it turns out that I've got them all on here, but it turns out that only two? Only two actually make it. So this one, option number 2 meets its deadline, or option 2 has all 4 tasks meet their deadline, and option 8 has all 4 tasks miss their deadline. All the other ones have at least one task that misses its deadline. Okay, so how do you, I mean, obviously you can't do a full enumeration because once you start having more tasks, because it's a factorial, gross is n factorial, right? So if I have a whole bunch of tasks, I can't go through a full enumeration. But there are rules of thumb you can use, like kind of, approaches that you can take. One approach is to do shortest task first. So prioritize the tasks based on their runtime. Well, it turns out that that doesn't work so well, because if we do task 2, that would be task 2, that's the shortest one, 6 milliseconds. Then we go to, let's see, task 3 would be next, 14 milliseconds. Then we go to task 4 is 20 milliseconds, and task 1. Yeah, I mean, I can prioritize them based on their execution time, but that doesn't work because task 4 misses its deadline, and task 1. We have 2 out of the 4 miss their deadline. How about earliest deadline first? That's another common approach. That one is you prioritize them based on their deadline. Whichever one has the shortest deadline, schedule that first. So if I do that, it would be, you look at the last column there, deadline. So I would do, I guess 4, or 3. 3 would be first because there's a 35 millisecond deadline. So 3, 4, 1, 2, right? So 3, 4, 1, 2. That actually works. In fact, that was one of the ones that worked. That was number 8. Another option is the least slack first. What's a slack? Slack is the deadline minus the execution time. So prioritize them based on that, and that actually worked out pretty well too. So yeah, that's not too bad. Those two, we found a solution, right? Okay, the problem is that, as you guys know, the deadline, it's not just running these tasks one time. The deadline is the period, the sampling, the control period, right? So it's the deadline is also the period at which you have to run it again, right? So these are called a periodic scheduling, which is where you have a deadline that you have to run the task and meet the deadline, but after the deadline elapses, you got to run the task again and meet the deadline. You guys with me? It's periodic. This is what you use for any controller, would have a periodic schedule, right? Just like you'll have this in Lab 4 with the motor, you're going to have to update the motor control after a certain amount of time and do it repeatedly according to a period. Okay, so in this case, the period is the same as the deadline. The period and the deadline are one and the same with a periodic schedule. So if you assume that you have one CPU and you've got a set of tasks, each task has an execution time and a period T sub I, P sub I. Tasks can now, here's the one thing. This thing can be preemptive or non-preemptive, meaning that you can allow a task to interrupt another one and take over, right? Or you could not allow that, right? Well, it turns out that if you don't allow tasks to interrupt, it becomes a much harder problem. So typically these will be, these are preemptible. You want the tasks to be able to interrupt. And you might say, well, under what circumstances would you allow that to happen? Well, it would happen if you have a task running and then another task's period ended. Or, I'm sorry, another task had a period that begins, right? And if that task whose period is now beginning has a higher priority than the one that was already running, you interrupt it. You put it to sleep temporarily, and you allow the other one to run, and then you can always go back and finish that one that was running. You guys with me? That's a preemptive system, right? You want to be able to preempt a task that's running. So we're going to assume that we have preemption because that's actually the simpler problem. And we want to find a schedule where no task misses a deadline. Okay? And another useful metric here is utilization, which is if you add up the ratios between the execution times and the periods. Now, and you might say, why didn't you do this before? Well, we didn't have periodic. When it's periodic, you can calculate the utilization. It's the sum of the execution time divided the periods, add them up. That's the total amount of time the processor has to work. You guys with me? Okay, so in other words, this would be 40 over 76 plus 6 over 84 plus 4 over 35 plus 20 over 37. You add those up and you get the utilization. Obviously, anything that's over 100% utilization is not feasible. And in fact, it is over 100% in this case. You end up with 153%. So this could never be done periodically. Now, we did it before because it was a one-off, right? It worked in the first example because we didn't repeat the tasks, right? But now we're going periodic. So this task set is not feasible, right? Okay, so there's two very common approaches for this, for how to do this scheduling. There's EDF, which stands for earliest deadline first. I mentioned that before, because earliest deadline first is always an option, even for non-periodic, right? Whoever's the earliest deadline. By the way, this applies to, I try to apply this in my own life. Like if I have a bunch of things to work on, which one do you choose to do? It's usually the one, whatever has the earliest deadline, you work on that. A good rule of thumb, right? Well, that's a scheduling policy for these, real-time periodic preemptible systems. There's also one called rate monotonic scheduling, which is basically you schedule the tasks with the shortest period first. Okay, so what both of these are is a priority scheme. These are both priority schemes. Basically, EDF is saying whichever task that's currently able to run that has the earliest deadline, it has the highest priority, so you give it the CPU. This one says any task that's ready to run that has the shortest period, that has the highest priority. Okay? So which one's better? Which one do we do? EDF, let's look at EDF. So this starts to get a little crazy. Let's look at 3 tasks. 10 milliseconds, period 40, 15 milliseconds, period 50, 5 milliseconds, period 20. Okay? Now these are periodic. The utilization is 80%. 10 over 40 plus 15 over 50 plus 5 over 20. So this can be done by utilizing the CPU 80%. I mean, the workload is 80%. Okay? Now the question is, can we schedule them? Well, here's why it gets crazy, because check this out. Task 1, 2, and 3 are shown on the timeline. I put red markers to show where each one's period starts. So I have to finish each one of these guys has to finish within its period, right? And so I've got this thing scheduled where after each period, every time a new period begins on any of the 3 tasks, you have to then make a decision about what you're going to do, right? So in this case, when I start out, which one has the shortest period? 3. So I'm going to do 3 first, right? Once 3 finishes, then what's next? Well, that would be task 1. That's 40, the next one, right? So I'll do 1, right? And then once I finish that, then I do task 2. Well, here's the problem. Task 2 doesn't get to finish. Task 2 doesn't get to finish because before task 2 finishes, task 3 starts a new period, right? And task 3 has a higher priority than task 2. So task 2 gets preempted. It gets put to sleep. So it's like, oh, sorry, go away. Now I got to do task 3 and finish him. And then when he gets done, I can finish task 2. Why? Because task 1 is done already within its period, right? You guys see that? Right? They all have different periods, right? So you have to look at which. So you have to clear each one of these guys' execution time within each one of its periods. But in this case, every time you get a new one starting, you have to reevaluate who you want to run, right? So task 3 interrupts task 2, and then the next one that comes up with a new period is, oh no, this gets bad. Look at this. Task 1 and 3 are monotonic, 1 and 3 are, yeah, these are harmonics of one another, right? So 3 has a 20 and this guy has a 40. So at 40, we have task 1 and 3 come up, ready to run at 40 milliseconds. So both of these guys are aligned. Which one do I choose? I choose 3 because he has a earlier deadline. Does that make sense? Okay, well that's basically it, right? Well, what's the downside of this? Does it work? Yeah, it turns out it always works. As long as your utilization is under 100%, this will always work. It'll schedule. No one will miss their deadlines. The problem is no one uses this. You might say, wait a minute, like what, wait, if it always works, why would no one use it? This has a serious downside to it. The downside is that every period, every time someone starts a new period, the operating system has to well, the scheduler, which is usually part of the operating system, the scheduler has to figure out what the priorities are of all 3 tasks after each one starts. So this is a dynamic scheduler. Priorities are constantly in flux, right? Because, see, like basically at this point, after task 3 finishes in its first period, task 2 has actually task 1 has the highest priority, right? And then when it finishes, task 2 has the highest priority, but at 20 milliseconds, it no longer has the highest priority. It gets demoted, right? Because task 3 becomes available for its next period, right? So who's calculating all this stuff? Well, the operating system, but it's expensive, right? Because you're going to add a lot of overhead to figure all this stuff out, and you're constantly having to reevaluate priorities. So no one uses EDF, even though it's perfect in the sense that it always works. So I try to show that here. So the priority of a task K is the period of task K minus the current cycle modulo the period of K, which basically the point here is that you have to reevaluate. The priority of every task is constantly changing as you go, as you run the scheduler. Rate monotonic scheduling, on the other hand, is simpler in that it's a static scheduling. You have static priorities where each task is oh, I'm out of time. Okay, sorry, 3:37. We'll finish this on next Monday, and then that'll be our last lecture, and then we'll have our review in 2 weeks, and then we'll be all done. And we'll see you in lab on Wednesday and Thursday. Thank you.